Hi, my name is Roberto Madini and I will present the paper Dash Strings and the Replace All Constraint. This is a joint work with Graham Gange and Peter Stuckey. So, what is the topic of this paper? The paper is about string constraint solving, which basically means solving combinatorial problems with string variables and constraints like concatenation, string length, membership to a regular language, and so on. So we take a string solving from a constraint programming perspective with Dash string formalism. And we focus on variants of the replace string constraint. The replaced constraint is frequently occurring in software and verification problems, but very few implementations are available in both the CP and SNT solver as well. We consider actually three variants of replace. Replace that replace the first occurrence of a query string Q in a target string X with a new string Q prime, replace last for the last occurrence of Q in X, and replace all that replaces all the occurrences of Q in X with a new string Q prime. And in all these cases, if Q does not occur in X, then we have X equal to Y, because basically we do not replace anything. So what are Dash strings? Fixed as an alphabet and maximum string length, Dash strings are basically simplified regular expression of this form, so a concatenation of blocks, where blocks consist of a set of characters and a cardinality, so a lower bound and an upper bound on each block. Let's see with an example. Let's consider these Dash strings, which is a concatenation of two blocks, and the concrete string denoted by these Dash strings are basically all the strings that starts with 1A or 2, followed by 0 to 3, B or C. We then propose a unified propagator based on Dash strings because, on the one hand, decomposing replace and replace last into basic constraint is possible, but it implies a loss of efficiency and precision. And on the other hand, replace all in general is not decomposable into basic constraints because we don't know a priori how many times a query string occurs in a target string. So we devised a propagator for all of these constraints. We implemented this propagator into gstrings, which is an extension of the well-known G-code solver with Dash string variables, so string variables with Dash string for the domain. And then we evaluated this new propagator against the decomposition approach and the state-of-the-art SNT solvers implementing the replace constraint. And results look good.
Alright, welcome to this talk about the argmax constraint. I'm Peter Stuckey and this is joint work with Graham Gange. So what is the argmax constraint and why is it important? So the argmax constraint we use is this example here. Z is the argmax of x1 to xn. And what is meant to mean is that Z is the index of the first position where the x variable takes the maximum value. And that first position is important because it makes it a function, and particularly for the first usage of argmax, which we'll talk about now, which is in encoding conditionals. So if you have this big conditional expression, if B1 then E1, else if B2 then E2, blah, 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 then you can actually encode that with argmax. So basically we're looking for the argmax of this Boolean list. The max will be true because the last element is true, that's the else branch. And so we'll find the index position of the first Boolean which is true. Then we use that to look up in the array of expressions the one that we mean to assign to x. So that's a very neat usage of argmax. An increasing use of argmax is because it appears typically in the last layer of some kind of classification machine learning model. So you have these scores, S1 to Sn, which are the score for each class I, and then you say C equals argmax of these, which gives you the class which has the maximum score. And that's typical in many machine learning models for classification. And in general, argmax allows you to embed an optimization problem as a subproblem and make use of its best answer. So max just gives you the maximum value that you can get out of the subproblem, but argmax allows you to understand which instance was the max and which was better. So what's wrong now? Well, there's no argmax propagator that we're aware of, and the current default implementation in Music is not domain consistent. So what have we done? We've built a domain consistent propagator and made an incremental one. In fact, it's easy to make it incremental. We've also found a new domain consistent decomposition which works for integers, and we show that the new propagation and the decomposition are better. And what surprised us was the decomposition actually beats the propagator in learning solvers in many cases. So just some quick results. So on unit tests we can get 2 orders of magnitude improvement over the existing decomposition. In some wireless signal selection where you use argmax to work out which tower a handset is connected to with argmax, you can get an order of magnitude improvement. And if we're doing minimal explanation of some boosted tree models and we want to use this, the actual model only has one argmax in it in a very large model, but we can still see a noticeable improvement by using either of the new methods. So in conclusion, we've implemented an argmax propagator for our solver. Well, you should go and implement an argmax propagator for your solver. If you're using Minizinc, you'll already be using the new decomposition. It was already included in earlier releases. And it allows CP to reason better about ML models.
Hello everyone, I'm Nicolas Zohar and I will talk about the work done with Jean-Charles Régin on the parallelization of the TSP solving in CP. The traveling salesman problem asks for data a list of cities and the distance between each pair of cities. This problem is constrained by 2 constraints. The first is to visit each city only once. The second is to find the shortest cycle. We propose to solve the TSP in parallel with embracingly parallel search or EPS. It decomposes the initial problem into P-independent and equivalent subproblems. Then, it solves them in parallel. In order to obtain P subproblems, it generates the search tree in breadth with an assignment limit. It iteratively increases the limit until the required number of subproblems is obtained. In the example, it's trying to obtain P equal 4 subproblems. The assignment limit is defined by the maximum number of left branches from a node to the root. It is first set to 2 and generates 3 subproblems. Since it wants more than 3, it increases the limit to 4 and gets 5, which is greater than P. The decomposition step is over. The search strategy used for solving the TSP, named LC first, selects one node from the graph according to a heuristic and keeps branching around the node until there are no more candidates around it, no matter if you backtrack or not. Let's take an example. Here, we set the assignment limit to 2 and obtain the subproblem represented by the blue search node. To do so, it branches AB and AC with A as LC node. The gray part represents the sequential execution, that is without assignment limit. As there are no more neighbors in A after the branching of AC, the search strategy selects D and branches around it in the whole gray area. Thus, to determine the LC node of the yellow part, we must know the previous one, which is A if we do a decomposition, D if we do a sequential execution. We can observe that the LC first is depth-based, while the decomposition of EPS is breadth-based. In the paper, we experimentally show that the combination of LC first and EPS at decomposition can give very bad results. To tackle this issue, we introduce bound backtrack and dive. It performs sequential solving with a bounded number of backtrack before doing the EPS decomposition. During the preprocessing, we set an importance of each LC node selected. Instead of selecting LC node with LC first while decomposing, we take the most important node having neighbors as LC node. This allows us to get almost a linear gain on the number of workers and often to considerably reduce the overall number of backtrack. To conclude, the integration of a learning strategy with EPS is not straightforward. Our algorithm allowed us to obtain good results and robustness. In the future, we would like to study the difference between the generated subproblems and focus on the load balancing problem for the TSP.
Good morning or afternoon everyone. My name is Margot Nataf and I am going to present a work done with Arnaud Malapert. This work is about filtering rules for flow time minimization in a parallel machine scheduling problem. Let's start with some context. The problem we are dealing with comes from the semiconductor industry. In this kind of industries, operations require a very high level of accuracy and need to be very precise. Therefore, machines have to be reliable and parameters have to be properly adjusted. The field dealing with the control of processes and equipment is called Advanced Process Control, or APC. In the literature, APC and scheduling are treated separately. However, they are interdependent. Indeed, to control, we need to know what is going to happen on the machine. And to schedule, we need to have information on the machine. Thus, the objective of the problem is to integrate APC, and more precisely APC constraints, into a scheduling problem. The problem we have considered can be divided into two parts, the scheduling part and the APC part. For the scheduling part, we consider a parallel machine scheduling problem with family setup time and machine qualification. And the objective is to minimize the flow time. For the APC part, we introduce a constraint called time constraint. This constraint limits the time between the execution of two jobs of the same family on the same machine. This is because each time a job of a family is scheduled on the machine, a measure is made. This measure allows to adjust the parameter of the machine if needed. Thus, if no job of the family is scheduled for a long amount of time, the parameter of the machine may not be properly adjusted anymore. So it is not possible to schedule jobs of this family on this machine anymore. The machine becomes disqualified for the family. The objective is to minimize the number of disqualifications. For this problem, several solving methods exist. 3 integer linear programs, 2 CP models, and 5 heuristics. We focus on exact methods because they outperform the heuristic. Among the exact methods, the performance are not equivalent. In a previous work, we showed that when the priority is given to minimizing the number of disqualification, then CP performs best. But when the priority is given to the flow time, ILP and CP have complementary behavior. Indeed, CP is able to find more feasible solutions, but ILP is able to prove more optima. Thus, the goal of this work is to improve the performance of the CP model for the flow time objective. And this will be done by propagating partial assignment to flow time. To briefly summarize our work, we study a relaxed version of the problem in which we do not consider time constraints anymore. For this problem, we define a polynomial time algorithm to optimally sequence jobs on one machine. Thus, if jobs are assigned to machine, the optimal flow time can be computed in polynomial time. Then, we use this algorithm to define 3 filtering rules. To define those rules, the idea is to consider partial assignment of job to machine, and then we try to extend this assignment by adding jobs to machine. The optimal flow time of this assignment is then computed, and the resulting lower bound is used to make decisions. In terms of performance, the filtering rules improve the performance of the CP model. Indeed, adding those rules allows us to prove more optima, around 80, and speed up the solving of the problem. In the comparison of the CP and the ILP, models show that CP is able to find more feasible solutions and better upper bounds, but ILP proves more optima than CP.